So let us calculate the number of states that the free electron can occupy. Now, because of the uncertainty principle, the smallest combination of space and momentum of the free electron must obey dx dp is equal to h, where h is Planck's constant. That means that the smallest volume that the electron can occupy would be dx cubed. Sorry, this should be a p here, not an x. It's going to be then h cubed over the dp cubed. So let's call this the smallest cell of space that an electron with a given momentum between p and p plus dp can occupy, right? This would be a cube of space of size equal to dx. So I'm using a different color. So you have an electron in here, in this space, and then this electron has momentum between p and p plus dp. Now, the number dn of such cells available is the volume VE that is occupied by the electron distribution. dn is the number of such cells, dx cubed is the volume of one of the single cells, and VE is the volume occupied by the electron distribution. So we can solve this for dn, and using the expression of the uncertainty principle, write that in terms of dp. Now, because of Pauli's exclusion principle, each of these cells can hold two electrons, one with a spin up and one with a spin down. That means that the number dGe, that's the degeneracy of the free electron, is equal to twice the number dn, because each one of these cells can occupy two electrons. Now, this number is infinitesimal because it captures only electrons with momentum between p and p plus dp. So for the total number of electrons, then we need to integrate in momentum. If we assume spherical symmetry in phase space, we can then write that d3 d cube p is equal to 4 pi p squared dp. And the volume of the electron distribution then is the inverse of the number density. Now, because this number is infinitesimal, it gives us only dni plus 1, not the full number of ions in the upper level. Can write this then as a differential of the number of ions in the upper level, the ionized state, over the number of ions, atoms in the ground state, is equal to Gi plus 1 times dGe, the differential of the degeneracy of the electron, over Gi, then the degeneracy of ions of atoms in the neutral state, and the exponential then of the energy in the upper state, the ionized state, minus the energy in the ground state, the neutral state. Now, if the ionized state, in the ionized state, the electron is unbounded, thus the energy Ei plus 1 is simply the kinetic energy of the free electron. And in the bound state, the electron had energy minus chi, where chi is the ionization potential. You had an electron in the ground state, it jumped not to an upper state, but it jumped to a free state. So what you have then is the ionization level, the ionization potential, that is chi, plus the kinetic energy of the free electron, which is p squared over 2m. So in fact, the energy I plus 1 minus Ei is equal to p squared over 2m plus the potential. So substituting this, you have then p squared over 2m plus chi in the difference of the energies. And if you substitute now the expression for the differential of the electron degeneracy, this expression still only gives the infinitesimal number of states where the free electron has momentum between p and p plus dp. We need to integrate this in momentum to find the total number of states. That means ni plus 1 over ni is equal to 1 over ni over the integral of the number of states in the ionized states, which is going to give us Gi plus 1 over Gi times 8 pi over the number density of the electrons over the cubic Planck constant times now the exponential of the ionization state over kT, and now the integral of all of the possible momenta. So this is a definite integral. Turns out that this gives you square root of pi over 4 times 2m kT to the power of 3/2. So you can substitute this, and then you find Ni plus 1 over Ni is equal to Gi plus 1 over Gi times 2 over NEH cubed exponential minus chi over kT times 2 pi m kT to the power 3/2. And we can express the ratio in the left-hand side in terms of number densities instead of total, dividing both sides by the electron density, to finally find Saha's ionization equation. Now for hydrogen, we already found that Gi plus 1 over Gi is equal to half. So this prefactor cuts. Simply have N for hydrogen then, 2 Gi plus 1 over Gi is equal to 1. Now the only states are Ni equal to N of hydrogen 1, which is the neutral state, and Ni plus 1 is N of hydrogen 2, which is the ionized state. And the number of electrons then is equal to the number of ions. Therefore, the Saha equation becomes N squared, the number of ions over the number of neutrals, is then equal to 2 pi mkt over h to the cube, and the exponential of minus chi to the minus chi over kT. So this solves the problem of ionization of hydrogen. To make sense of the number, let's write the ionization fraction. Let's define the ionization fraction, call it x, as the number of hydrogen ions over the total number of atoms, which is H1 plus and H2. So we have an equation for the square of the number of ions over the number of neutrals. You can write that in terms of the ionization fraction. It comes in square of the ions over the n of the neutrals. If you define NH as equal to the number of the total number of hydrogens is the number of neutrals and ions, then you can write the number of neutrals as the total number of hydrogen minus the number of ions. Now extract the number of hydrogen atoms so that everything is divided by it. And that is the ionization fraction in there. So what you have here in the end is the total number of hydrogen atoms over x squared minus 1 minus x over 1 minus x. So Saha's equation is giving you that quantity here, n squared, n of hydrogen, x squared over 1 minus x. Now the number density in terms of the mass density is rho over the mass of the hydrogen atom. So we can write this equation as square the number of ions over the square over the number of ions over the number of neutrals is equal to rho over the mass of hydrogen times x squared over 1 minus x. So this equation is a quadratic. If you multiply and divide both sides by mh over rho, then what you have is, now if you call what is in the left-hand side alpha, this equation simply then becomes x squared plus alpha x minus alpha is equal to 0, or alpha then is equal to. So we can solve this quadratic. The quadratic is simply square root of alpha squared plus 4 alpha minus alpha over 2, the quadratic formula, where we discarded the unphysical negative root. Now the solution to this equation for a set of densities is shown here using the ionization potential of hydrogen, which is 13.6 electron volts. You see here, it depends on the density. These are the curves for the blue is 10 to the minus 9, 10 to the minus 10, 10 to the minus 11, and 10 to the minus 12 grams per cubic centimeter. you start to see here that for densities of about the sun, which is 10 to minus 9, you have at 10,000 Kelvin about half of the atoms being ionized, as we saw before. So if you combine this with the curve of excitation, so the excitation was this one. You have here the number of atoms in the ground state and the number of atoms in the first excited state. They cross at about 10 to the 5. But at 10 to the 4 Kelvin, you start to ionize really heavily. Now, if you combine them both, excitation and ionization, this is the curve that you have, peaking at 10,000 Kelvin. This is, again, the curve for different densities. For solar densities about 10 to the minus 9, you start to have ionization and the excitation and ionization balance peaking at about 10,000 Kelvin, as you see here. So that gives you the maximum strength of the Balmer lines.